So hello, good morning. It is a pleasure to have you here, and it's a pleasure to have Professor Thomas Webster with us. Tom studied at chemical engineering, and later he did a PhD in biomedical engineering at RPI, and he has been a professor in several universities such as Purdue, Brown, and Northeastern University. Actually, he was the chair of the chemical engineering department when I went there, and we started a collaboration. And he has founded about a dozen companies, and he's involved in many of these companies as the scientific officer. And his accomplishments are huge, and he's been the president of the Biomaterial institution in the United States, and his H index is above 100, so it's impressive. And we are very happy to have you here with us today, Tom.
Yeah.
So please,
excellent.
The floor is yours. Thank you.
Yeah, thank you, Jose, for that very nice introduction. And it was a great pleasure having you in the lab, and hopefully we'll be able to continue to collaborate in this area of nanotechnology. So I brought a little festiveness with me, my Hawaiian shirt. I knew you're in this incredible heat wave here in Europe, so I thought I would join with that. So just to give you a little bit of an update on what I'm doing now, as Jose mentioned, he had a Fulbright fellowship and worked in the lab on a couple of projects when I was at Northeastern. I have left Northeastern. I'm still affiliated and teaching classes at some universities, but for the most part, I'm focusing on the research that developed through my labs. I can't believe it, I guess over the past 25 years, and trying to commercialize as much as we can. So I'm not at the end of my career by any means, but I see this as an important, step to develop things in the lab and then to commercialize them into real products, hopefully. So having said that, here are three companies that I'm going to talk about today. Interstellar Therapeutics, I love the space age name for it. NanoV is actually one of the oldest companies that formed when I was a professor at Purdue University, and then Audix Medical. I'm actually going to start with Audix Medical because I want to talk about COVID, believe it or not. Maybe I'm one of the few people who wants to talk about COVID. But so in the US, and I think you do this in Europe too, a lot of times we have to give disclosures. So I do have a financial interest in all of those companies. I'm the chief scientific officer for these companies, and it's because they licensed research from my academic lab. So let me just disclose that to you in the beginning. And again, I want to start off with COVID. I didn't anticipate talking about COVID here, but I think it's important. I think it's important to discuss how we as researchers are trying to help in the COVID situation. So I think what's also very important about this subject is to always analyze how we got here in the first place. I think we tend to survive a disease, a pandemic, and never really think about what caused this in the first place. And I think unless we acknowledge that something went wrong here, clearly, if you have to tell people to stay home as the only way to keep a virus from spreading, I think something went wrong. So I think we have to acknowledge that. We have to talk about what went wrong, and then we have to come up with solutions for what went wrong. So here's my list of what went wrong for COVID. And certainly I encourage you to offer your ideas, your opinions, because again, unless we do this as a scientific community, we're never going to have solutions. So I don't think I'm really saying anything all that controversial, I hope not, to state that our global healthcare system failed. And again, I just think of it very simply. If the only way to keep a virus from spreading is to tell people not to interact, that's a failure. And healthcare systems are set up in each country around the world. As we know from COVID, everything is so interconnected in our healthcare systems. What happens here in Spain will eventually affect the United States and vice versa. So we are all interconnected, yet we do such a poor job of communicating healthcare systems, positives, negatives with each other. So I think COVID really, here's my list of things that really went wrong due to COVID. And I think what COVID has done is it really highlighted this inefficiencies in our healthcare system. I think it highlighted failures in our healthcare system. So let me just mention a couple of these. I think we all remember those videos of overcrowded hospitals, patients in the hallway, lines going out the door of hospitals for people who were sick and didn't know what to do. I actually think our whole idea of a building that represents healthcare is old-fashioned. I think we need to do a much better job of just getting away from this idea, here's a hospital, that's where you go for healthcare. I think what we need to do is bring healthcare to you, the patient, wherever you are, at home, at work, at an amusement park, wherever it is. We need to do a much better job of enabling you to figure out your own healthcare system and get rid of this antiquated idea of a hospital. I think also there's been a lot of barriers throughout this COVID situation that kept people from getting healthcare in the first place. And of course, there are geographical barriers. How close do you live to a hospital? There's economic barriers. Maybe your healthcare system in your country does not support you, or it's too expensive to get good healthcare, like perhaps it is in the United States. And also, one thing we don't talk about a lot, psychological barriers. There's been a lot of studies throughout COVID suggesting if you're a male, Caucasian, over 50, I'm over 50, I know it's hard to believe, I'm less likely to go for any healthcare than other races, other sexes, other ages. So how do you help someone like me? Fortunately, I'm not like that. I do go in for healthcare quite frequently and get checkups. But we have to figure out how to get to that person, how to help that person, because again, we're all interconnected. I've spent a lifetime about medical device failures. And yes, hip implants, pacemakers, vascular stents have improved the quality of life of millions, but they still fail. We still have functional lifetimes of every implant that's used in the body. So we still don't perfectly understand how the human body interacts with tissues to have 100% non-failure rates. I think also a big problem in our healthcare system is we tend to think drugs will solve everything. Antibiotic-resistant bacteria is a great example of this. If you have an infection, let's give you an antibiotic. And of course, as we know, now bacteria have developed resistances to some antibiotics that we can't kill. MRSA, great example. MRSA, Staphylococcus epidermidis, resistant strain. I think in the US, we're suffering from the opioid epidemic. You go in to get a surgery, you get prescribed painkillers, opioids, and then a number of people are becoming addicted. After their prescription runs out, they go look for illegal drugs. So this idea that drugs will fix everything in our healthcare system, I think is also problematic. We also tend to treat every patient the same, but if I fall down and break my hip, that gives me a different reason to want a hip implant than somebody who had bone cancer and a tumor was removed and then needs an implant. So we have to treat people much more individualistic for their particular problems. We have different immune systems. The person next to you has slightly different immune systems because of what you've been exposed to throughout your life. So why would we give the same treatment to everybody? This is a huge one. Our healthcare system is very reactionary. You have a problem, again, you go into this old-fashioned hospital, somebody tells you what that problem is. That reacts. What other field works this way? When you drive over a bridge, I hope they're not only fixing that bridge after it fails. I hope that there's some preventative assessment of cracks and mechanical strength before you actually drive over a bridge. So of course, all of this inefficiency in our healthcare system, I think, leads to increasing costs. We have a growing global population. So, many of us years ago turned to nanotechnology as perhaps an answer. And the field is still strong, right, as we know from your institute today. And this is wonderful. We are still learning so much about nanoparticles, nanotubes, self-assembled nanomaterials, nanotextures, all of this family of nanomaterials. We are still learning a lot. One thing we know throughout all of this research that everybody is doing around the world, cell behavior can be controlled through nanotechnology, and that is very powerful. Without a drug, you can control cell function through nanotechnology. You can kill a virus. You can kill bacteria. You can kill a cancer cell. You can grow bone. And this is very exciting to me. So still, we have a lot more to learn about this field. There are certainly still a lot of negatives about nanotechnology, but the field, the positives are really pushing, I think, everybody towards looking at more and more nanotechnology applications in health. So I wanted to spend a couple of minutes just maybe introducing to you, refreshing your memory, that nanotechnology has really been front and center in helping us get through COVID-19. And I'm not sure if you're aware of this. You might not think about it that much. But I think about every disease. How do you prevent that disease? How do you diagnose that disease? And then ultimately a therapy. How are you going to treat that disease? Nanotechnology has been in every aspect of this for COVID-19. So I don't know if anybody's wearing a mask that has metal nanoparticles, but you can commercially buy masks that have metal oxide nanoparticles. And the reason that these are being sold and these are being used is studies have shown that these metal oxides that are impregnated into a mask will release reactive oxygen species once they get wet. So you cough, a virus comes out, gets wet, you now have reactive oxygen species. Here's a diagram of SARS-CoV-2, obviously the virus that causes COVID. That reactive oxygen species breaks down the envelope protein that holds the RNA. You destroy the virus. So this is great, right? So you don't just have to think about a mask protecting and trapping the virus, but you can think about the mask passivating the virus. Same thing with everyday surfaces. So people are decorating everyday surfaces with nanoparticles. We've been doing this for aluminum. Here's uncoated aluminum. We happen to like a chemistry selenium to deposit a surface, precipitate selenium onto a surface. That selenium can also produce reactive oxygen species, and that can cause virus passivation. So if you touch that surface, you're not picking up an active virus, but a deactivated virus. There's other technologies that people are commercializing, like TiO2, which can be decorated on surfaces activated by UV light. That produces reactive oxygen species. That passivates SARS-CoV-2 on handles, doorknobs, whatever you might want to think of. Diagnostic kits. So magnetic nanoparticles like iron oxide. If you functionalize them with a region that attracts to SARS-CoV-2 and then you apply a magnet, you can consolidate the virus. That makes it much easier to detect a small level of virus. So there are kits that you can use that use magnetic nanoparticles to help with sensitivity. But this is really the area that we have focused in. And this is where the company Audex has been making self-assembled chemistries that can passivate SARS-CoV-2. So I don't mean to insult anybody's intelligence, but let me show you a real simple video that kind of describes this self-assembled nanomaterial. So that's how it normally works.
The self-assembled nanomolecule can attach to the virus surface protein. This would keep the virus from attaching to a cell, entering the cell, and replicating.
So obviously, it's a simple block that we're doing, right? We are developing this material, have it attached to the virus, that keeps it from getting into a mammalian cell, and that's naturally how a virus replicates. It attaches to what's called the ACE2 receptor of a mammalian cell, gets in there, and then replicates. Many technologies today, those developed by Big Pharma, are really looking at stopping virus replication inside the cell. There's a lot of enzymes you can control, a lot of events. Our approach has been keep it from getting inside the cell in the first place. It's more challenging to do this because this has to be really specific. The molecule we're developing needs to attach to the virus, not a fibroblast, not a blood cell, not something else in the body. So it's hard, but if you can do it, you stop all replication from occurring. If you're targeting things inside the cell, some replication will occur and then you stop it. So we think it's more efficient to do that. So what's the molecule? And sometimes we call it the blanket, right? We're blanketing the virus, inhibiting it from attaching to a cell. This is the chemistry that we have been exploring for probably about 10 years. So back when I was at Brown University, we developed this chemistry in collaboration with a colleague of mine, Hisham Faniri, who just took a new position in Morocco, which would be great to connect some people with his supramolecular chemistry research in Morocco. We developed a DNA base pair self-assembled material. If you want a material to self-assemble, looking at DNA is great, because as we know, DNA self-assembles into this spiral. So we took guanine and cytosine, 2 DNA base pairs, made this new molecule, has great electron donor acceptor complementary regions. So 6 of these things get together and they make a ring. They self-assemble all by hydrogen bonds. This will also, at a high enough concentration, self-assemble into a sphere. At an even higher concentration, you can get tubes, nanotubes that are hollow. And we've done a whole bunch of tissue engineering work on these molecules where you can put anti-cancer drugs down the inside of these tubes, antibiotics, pro-bone growth factors, and you can get very slow release, which is great for drug delivery. So this molecule has a lysine side chain. You can change this. This is for tissue engineering because osteoblasts, cartilage cells, all those cells love lysine. In fact, if you do cell culture, you coat the bottom of a petri dish with lysine, you'll get a lot of cells to attach. We don't want that for COVID. We definitely want that for tissue engineering, where we're developing this material, injecting it into bone defects, cartilage defects to regenerate those tissues, but we want to replace this. So back when COVID started in China in 2019, I have a lot of colleagues, as you probably notice, I'm part of a university in China, which is starting a biomedical engineering program. They were telling us, get ready. Some people were a little bit naive. This will never come here. This will never affect me. But we started thinking about this very early on. And we started thinking, what do we replace that lysine side chain with that enables our self-assembled molecule to attach to SARS-CoV-2? Fortunately, at that time, there were studies telling us what the amino acid sequence is of different proteins on SARS-CoV-2. Now, most people are super concerned with the spike protein. And that makes perfect sense because the spike protein is what attaches to the cell. However, we knew from other coronaviruses like MERS, the Middle Eastern Respiratory Syndrome, if you remember when that occurred, and some other coronaviruses, this is where all the mutations occur. And guess what's happened since the first strain came out, which is commonly called the Wuhan strain? Every mutation since then significantly mutates in the spike protein. So we said, well, do we really want to target something that's mutating? No. So we looked at a different protein, this envelope protein. There still is some mutation that occurs in all of these strains for the envelope protein, but it's much less than the spike protein. So we said if we can get our self-assembled molecule to attach to the envelope protein, that would be a much more stable, much more mutation-resistant approach. So we looked up, some of our virologist friends published the amino acid sequence of that envelope protein, and we just used our chemical minds to come up with complementary peptides that would have a charge attraction to that peptide. So if there was a hydrophobic peptide, we would put in there a different peptide that's hydrophobic, that would have an attraction to it. Okay? So we built probably about 50 different peptide sequences as possible candidates that could be put on SARS-CoV-2. Now, the one thing that happened, and I think this is a big problem actually, is then in the US around February, March, things started going crazy. I think here it was a little bit earlier than that. Our labs were shut down. So at this time, I was at Northeastern University. Just like you guys, everybody was sent home. Do not come into the lab. So we said, okay, great. We think we have an approach that can work for SARS-CoV-2. We have no way to test it. And I think this is something we have to think about in the future, is if you're sending scientists home, and I know this is controversial, but you send scientists home who might have a solution, are you hurting yourself in generating a solution? So unfortunately, Northeastern just did not allow researchers to come back. So we used computational modeling, molecular dynamics. You can do that at home. We did it at home with our computers. And we looked at things like, all these peptides, Gibbs free energy, electrostatic forces, van der Waals forces. We basically tried to figure out which peptide's the best to study. And through molecular modeling, we figured that out. We figured out, and here it says peptide 6. That's this one, if you're interested in the chemistry, is the one that showed the best function. So weeks went on. We did this in about 2 days. Weeks went on. We still could not get into the lab. We were getting super frustrated. So, we worked around the system and we spun this out into a company. As I mentioned, Audix. Companies could still do research. So we made peptide 6 in the lab. We put it onto our self-assembled molecule, and we did what's called pseudovirus experiments. So pseudovirus experiments can be done in a biolevel safety 2 lab. You don't have to put on the spacesuit and be like, the Centers for Disease Control in Atlanta to do studies. Do these very easily in a nice lab. And they are viruses that replicate just once. So they are genetically modified from the real virus because they only replicate once, and that's why they can be done in a safe environment. So a lot of companies make pseudoviruses. We didn't make them ourselves. We used Creative Diagnostic as a company. How these assays work is you culture the pseudovirus with cells, mammalian cells. The more fluorescence intensity, the more the virus is replicating. We then, of course, added our molecule. So the different colors are different concentrations of our molecule. So we went from 1 milligram per ml down to 1 microgram per ml. We also looked at different pseudovirus concentrations from 10 copies per microliter up to 1 million copies per microliter. And we tried to do this experiment as fast as humanly possible. So this is for 15 minutes. That this culture of the pseudovirus with the mammalian cell and our molecule occurred. So we were super excited because with the Wuhan strain, we saw upwards of 83% inhibition, so we stopped about 83% of the virus from replicating. So pretty good after just 15 minutes. Of course, as we all know, the virus mutated. One of the ones you might not remember, the variant B117, came up very quickly. We used the same molecule, the same assay, just with the different pseudovirus, and we got the same result. And again, this is because we targeted the envelope protein, which wasn't mutating. We didn't target the spike protein. Again, mutation, variant 501YV2, same exact result, same exact molecule. You probably remember the Delta variant when it came along. Same exact molecule, same exact result. This is Omicron, but this is not the current Omicron that's creating a problem. This is Omicron BA2. The one that's creating a problem now, I think, are 2 strains, BA4 and BA5. So in fact, I don't know if you know this, but there's a study that was published last week in the New England Journal of Medicine that the vaccines, a lot of the vaccines are not effective against Omicron BA4 and Omicron BA5. But this was Omicron BA2. Still saw great inhibition. Actually, we saw greater inhibition. We think that might be because the mutation was in favor of our molecule, attaching to it and masking it. So that was wonderful. We also started looking at other viruses. So not just SARS-CoV-2, but how does our molecule perform with HIV, influenza, B and A, right? Rhinovirus, that's the common cold. We have nothing. You have to suffer through a common cold, right? We don't have anything that helps with rhinovirus. And these are just other coronaviruses. This is computational modeling. We do have some experimental results that I don't have time to share with you. But you can see here, negative means the higher the negative, the more it's attracted to it. So very high attachment strengths. And what's really interesting to us is all of these viruses have different structures, right? So a rhinovirus has like capsid type surfaces. They don't have that spike protein. So we think, this is something could be very special, that the same molecule does have a charge attraction to multiple viruses. And I would say, too, one failure of our system in dealing with COVID-19 and SARS-CoV-2, we didn't really have versatile approaches If you remember when all of this started, people just said, wait for your vaccine, right? Go home, stay away from people, wait for your vaccine. That means we didn't have anything versatile that we could easily attach a different region to passivate that virus. So we need a lot more work in more versatile molecules that can be used for many different viruses and passivating those. So of course, the other thing I wanted to share with you is whenever you do biomaterials work, nanoparticle medicine work, you have to do animal studies, right? So it's very important to see, does all of this petri dish stuff translate into an animal? So Audix works very closely with the FDA. The preferred model that the FDA suggests are actually hamsters. The hamsters don't die. Maybe we should be studying them a little bit more. They don't die from COVID-19. They get symptoms and viral loads very similar to humans in the lungs and in the nasal passages, but they don't die. So we used the hamster model. We used a company called Southern Research Institute in the United States. We looked at different doses. We looked at the Delta strain. We're currently repeating this for the Omicron strain, BA4 and BA5. We'd used a critical challenge, so we used enough viruses that this would create a significant viral load in the lungs of the hamster. Oh, we used intranasal. That's the other important thing, is we think intranasal is the way to go for this virus because that's a direct route to your lungs where there's a lot of problems. So this was a drip. You can aerosolize these molecules, but this was more of a drip that was used for the animals. We also used a preventative measure, so the animals had our molecule first and then the virus, or we use it as a therapy. Virus first and then our molecule, so prophylactic therapy. Of course, we have controls. This y-axis is the number of RNA in the lung of the hamster after 4 days. And what we saw, as you can see, is a half-log reduction when using either a preventative method or a treatment method. So this is good. This is, if you're thinking of a grade in class, maybe this is a B. We want an A. So we think we use too small of a concentration, so we're increasing that. We're also increasing frequency. If you look at some of the drugs that exist today from Pfizer that can be used as a therapy after you test positive, their concentrations are much higher. So we think we have a lot of leg room to increase that. However, clinically, in the literature, you do see a half-log reduction in viral load can improve your health. So we're on the right path. The other thing we did, and this gets more into the mechanism, remember we're targeting the virus outside the cell, is you can look at a different kind of RNA for SARS-CoV-2. It's called guide RNA. This measures an unprocessed RNA. So this is the original RNA that was added to the animal, not the replicated RNA. So of the lower amounts of RNA that I just showed you, most of it was a unprocessed RNA in the animal. So what that means is, in fact, most of the RNA we measured is outside the cell. So that's great because that shows that it was not replicating RNA that was in our study. And the last thing I want to share with you about COVID-19 before moving into some other nano efforts that we have going on is nanotechnology has been front and center in vaccines too. So this is Moderna. Moderna is one of the most popular vaccines in the United States. Moderna uses a lipid nanoparticle to deliver its RNA approach, its mRNA approach. So this is wonderful because people have been researching liposomes for decades, for cancer work, delivering a drug to a tumor, for infection work, delivering an antibiotic to an infection. And now all of that was helpful in Moderna being able to develop a vaccine out of that lipid nanoparticle. So that was incredibly exciting, I think, to see as somebody who's been in this field for a while. Okay, so let me quickly transition. So I think probably if you think about all the nanomaterials, you might not even consider self-assembled materials as a nanomaterial, right? You would say nanoparticle, nanotube, maybe all those different geometries, but you might not even think about self-assembled materials. So I wanted to highlight just some of the work we've done through the years on nanotextures. And we have seen this to be easy to get through regulatory agencies like the FDA in the US, where if you're not changing chemistry, but you're only changing nanotexture to improve cell functions, you can get very quick regulatory approval. So that's great from a commercial point of view. That means you can really get an improved implant quickly through the FDA to the patient. So we have work in spinal cages that have been 3D printed, create nanotextures. We call this one Hive 3, like a beehive. We have work where we're using amputee models. So this is a rat study where you have a screw that's been anodized. If this were, a real amputee model, you would fit the plastic prosthetic onto the screw. It's called an osseointegrated amputee model. That screw, when having a nanotexture, results in wound closure. So these screws stick out of the animal or the patient. So skin closure is very important. In the controls, we don't have skin closure. This is where bacteria goes. This is where inflammation occurs. This is where you can get bone non-unions. So just putting a nanotexture on that material improves the function of an amputee device. In fact, this spun out into Nanovi, the company I mentioned before. Nanovi is making spinal screws out of these materials that were anodized to have that nanotexture. There's been about 3,000, I think 250 implants in humans for these screws, but who's counting? And so far there's 0 infections. So that is great news to us that we're not seeing any colonization of bacteria. We're seeing all bone growth occur next to these. So that's wonderful progress that we hope we're able to reduce the use of antibiotics by making materials like that. We also have efforts where we've grown tendons, ligaments, orthopedic soft tissue off of metals that are nanotextured to improve tissue growth. Vascular grafts, put nanotextures on vascular grafts and you can increase endothelialization or artery regeneration. Catheters that have nanotextures, we've seen that reduce bacteria attachment and infection. There's nothing worse than getting an infection from a catheter because then you've infected your whole body, obviously. We've used nanotextures for things like magnesium oxide. I'm not sure if you're familiar that much with magnesium oxide. It's biodegradable, but a problem is it degrades into hydrogen gas. Who wants hydrogen gas in them, right? If you develop a implant at a magnesium oxide, what we have seen, you nanotexture magnesium oxide, you can decrease the generation of hydrogen gas. So you're able to actually reduce the toxic hydrogen gas that's generated and increase tissue growth. So even nanotexturing biodegradable materials seems to be a nice future area. So why? Why is all this happening? And we could talk forever about this and even ask why on top of why on top of why. But here's what we think are the major mechanisms for why nanotextures are improving tissue growth, decreasing infection, decreasing inflammation without drugs. First of all, you find them all everywhere in nature, right? If you took your electron microscope, took an insect wing, you find nanotextures on an insect wing. Bacteria don't attach to the wing of some insects. So this nanotexture that's present can be easily copied over to medical devices to reduce the bacteria colonization. We could also talk about biophysical models. So this is a bacteria, about 1 micron in dimension. Its membrane is too stiff to fit all of these contours, so it doesn't attach. If it doesn't attach, your immune system is much more likely to kill it. If it attaches and grows, that's a biofilm, and that's a problem. We have been spending most of our time looking at the reason why for surface energy. If you put nanotextures of the same chemistry on a material compared to a micron texture, you can change energy. You can change contact angles. You can change hydrophilicity. And you can either make it more hydrophobic or more hydrophilic depending on the dimension of that nanotexture. So why is that important? That interacts differently with proteins. So this is an AFM study. This is nanotextures of polylactic glycolic acid, a biodegradable polymer approved by the FDA. Fibronectin adsorbed to nanotextures, same chemistry but micron textures. Here's fibronectin adsorption. Fibronectin adsorbed to micron textures like a blob. Very scientific term. So this is non-bioactive. If you see a protein adsorbed like this, it's not bioactive. If it adsorbs like this, fibronectin, it's starting to stretch. It's becoming more fibrillar. It's exposing more amino acids, which cells can attach to. So not only can nanotextures give you the surface energy to absorb more of the protein you want, but it can also change its bioactivity to make it more powerful for that application. In fact, we've created an equation. I'll spare you the calculus on this. But the equation can tell you the height, the width, and length of a nanofeature to put on a material to increase absorption of a protein you want. And maybe you want fibronectin to increase tissue growth. Maybe you want to absorb a protein in your saliva called mucin, which will decrease bacteria growth. Maybe you want to absorb more of a protein called lubricin. Lubricin is in your joints. It helps lubricate your joints. So maybe if you have osteoarthritis and feeling a lot of pain, you could develop a biomaterial to increase the absorption of lubricin, to lubricate that joint. There are many, many different kinds of applications. And as you mentioned, nanotextures alone can go this way or it can go that way. And you can think about a ton of non-biological applications for this too, including one that we just started working with, a company that makes windmills. So they said they were suffering a lot from ice buildup, and then the windmill goes slower. So what we've done is we've generated nanotextures on a windmill that reduces ice formation. So instead of somebody having to de-ice your airplane wing, and you're sitting there, that probably doesn't happen too often in Spain, happens a lot in Boston. But you can now create textures that could decrease water absorption. You decrease water absorption, you decrease ice formation. So this idea can really go so many different ways. Okay, so let me introduce another thing we're working on that I think needs a lot more attention, this area. So I know it's a lot of text up here, but in short, to me, biomaterials and nanotechnology have been some of the last research areas, last commercial areas to embrace green technologies. If you look around every other technology, automobiles, consumer products for your dish detergent, that have the green symbol on them. For some reason in medicine, maybe because we're treating patients, we think it's okay to harm the environment in doing so. I'm not sure why. It's just been so slow. But my research is to blame too, right? We've looked at things like titanium, right? I showed you titanium. We've looked at stainless steel. We've looked at polymers. All of these things create huge environmental problems. So, a couple of statistics on the contribution of biomaterials to global warming is these materials are commonly used in medical devices. So whether it's the energy used to manufacture these materials, the byproduct chemistries you get when you make them, or you consider the plastic island that's in the Pacific that I'm sure you're all aware of. A study recently said about 5% of that plastic island are catheters, polymeric catheters. They don't degrade, right? We're not creating them out of any kind of environmental free, most catheters are polyvinyl chloride, right? Same thing pipes, plastic pipes are made out of. So anyway, lots of statistics that you can see about the problem here. I think too, this is only growing as the medical device field grows. The contribution of medical devices to these plastics that don't degrade is a big problem that we need to really deal with. So how are we part of this? We're actually trying, green chemistry or green nanomedicine, as we like to call it, can mean different things to different people. How I think of green technologies is you're using less energy to make something. You're making something out of a natural material, or it's less toxic. You're using less toxic chemistries when making it. If you've ever made a nanoparticle, and I'm sure you have, some of them, when you make them synthetically, actually use toxic chemistries. So even in nanotechnology, where we think we're doing a lot of good, we're still contributing to the use of toxic chemistries. So a project, a couple of students that, Jose, you were helpful with, were actually thought of this and came up with approaches that, okay, let's forget about synthetic chemistry as a way to make nanoparticles. Yes, let's use cells to make nanoparticles. Cells can make nanoparticles, and they can do so without toxic chemistries. So the toxic chemistry you use to make gold nanoparticles, you can use a cell instead. Just add the right metal salt in the culture of cells, and those cells can be bacteria, they can be mammalian cells, fibroblasts, endothelial cells, whatever. You can actually give the right starting material, and inside the cell you will get nanoparticles, and some of those nanoparticles will be excreted, and you can use them in biomedical applications. So one particular chemistry, as I mentioned before, we're interested in is selenium. So this particular student made nanoparticles of selenium by culturing the selenium salts with Staphylococcus aureus. So we know we're reducing the need for toxic chemistry, but what is also interesting, and this happens a lot in green chemistry and other fields, the particles produced by cells are better than the particles made synthetically. And maybe that's because they're not using the toxic chemical, or maybe it's because of this. When those particles are made by living cells, they're made with a protein layer. We often call this the protein corona in nanomedicine. This protein layer comes from the cell that made it. So how we're leveraging this is these nanoparticles made by Staphylococcus aureus have proteins that help target this particle to that bacteria. So in other words, and consider this, right? So you have a lot of good bacteria in your body, and it's all right here. It helps you digest food. You don't want to kill that bacteria. You want to kill the bacteria that should not be there, like a Staphylococcus aureus or a methicillin-resistant Staphylococcus aureus, MRSA. So if you use that bacteria to make that nanoparticle, naturally it will have proteins to target that bacteria, to kill that bacteria. And that's exactly what we're seeing, is the bacteria, we're programming bacteria, like, there's another one for E. coli that made nanoparticles of selenium. And then what we're seeing, and I won't go through this data, but we're seeing that those particles are more effective at killing the cell that made it. And the same thing is working for cancer, too. If we have a breast cancer cell make a selenium nanoparticle, that particle is much more effective at killing breast cancer than those made synthetically. So hopefully that's kind of a contribution. This is an animal study that I'll skip. In short, I'll say that we coated orthopedic materials with nanoparticles of selenium. We forced an infection in a rat model, and we saw decreased MRSA colony-forming units on the coated, selenium-coated material. And at MRSA, which is Staphylococcus epidermidis that's resistant to methicillin, that colonization was smaller as well. And it wasn't just on the surface of the screw, but it was a certain distance away. So a lot of times when you get bacteria infection, it's not just on the implant, but you get a lot of bacteria a little bit away. So the distance away from that was also important. Okay, so the last part that I wanted to introduce too is I love nanotexturing. Absolutely love it, right? Simple. There are so many techniques that can create nanotextures. So effective, we see, so easy to get through the FDA and get into patients. You don't have to wait 10 years to really help a patient by doing nanotexturing. But I do not think in 10 years from now, this will be the biggest contribution of nanotechnology. It can't be. We need much more proactive materials. Remember that list of problems in our healthcare system? We need materials that respond to you and how you're responding to the implant, right? Some people get inflammation around a hip implant. Some people don't. We need to figure out who's going to have inflammation and then have the implant change to enable that to happen. So here's two ways that we're creating intelligent materials. One we call 4D printing. I think we all know what 3D printing is. The fourth D is time. So the idea is you 3D print a material. So here we 3D printed that same self-assembled material I showed you in the beginning. Flower, hand, body, brain, heart. If you then 3D print these with graphene nanoparticles, they turn black. Graphene's black. Graphene responds to near-infrared. So near-infrared can heat up graphene. You can heat up these graphene nanoparticles in a controllable way and change dimension at a distance with time, anytime you want. So, fortunately, we omitted one particular finger in this. But we could have our hand, pay a nice compliment to somebody at any time we want. So how is this useful, right? This 4D printing where you're putting a nanoparticle in a 3D printed material and then controlling its shape with time. Well, here's just a couple of examples that I can show you. One is stem cell delivery, and this video will just play, but it'll show a shape change. The big problem with stem cell delivery is when you culture cells on a petri dish, you have to get them off to put them in the body. A lot of cells die in that process. In contrast, if you use a 4D printed material, you printed it into a flat cell culture surface, you put stem cells on there, you use temperature or you use this near-infrared idea to curve it into a tube, you can now take that and implant it. And that's what we're doing with a colleague from Mass General Hospital in Boston, is delivering neural stem cells in this manner. So you don't have to lift them, you don't kill any cells, because you're simply changing shape using some kind of external environment. These graphs are just showing before shape change, after shape change. You're not killing the cells at all. You're maintaining the function of a neuron in terms of neurites, in terms of function of regenerating neural activity. But that's not the only one, and I don't have time to go into all of these applications. One of the ones that we're super excited about, and this is being commercialized by Interstellar Therapeutics, is scoliosis. If you've ever known somebody, and they're usually children, obviously, who go through scoliosis treatment, it is the most aggressive, debilitating treatment that's out there. They have to have rod after rod after rod, spinal rod implanted as the spine slowly straightens. It is incredibly painful for the patient. It's slow. So our idea is use these self-assembled materials, these 4D printed materials, inject it next to the spine, have it attached to the spine, and then use your near-infrared control to slowly or quickly straighten the spine. So then you don't need all these repeated surgeries. Another one we're very excited about is in the intervertebral disc. Bone grows under increased pressure. Inject into the disc. Have 4D control over swelling. If bone is not growing, the material swells, puts pressure on those bone cells. Sphincters. Acid reflux, right? Your sphincters, you have a lot of them in your body. They slow down contraction with age. So something like acid reflux. We have a project where you're creating this material, put it in where it keeps the acid from the stomach going back up into the esophagus. So you can close and open on demand using this system. And I just mentioned stem cell delivery too. Okay, so I'm not going to show these, but let me just end with this example, because this is also, I think, where nanotechnology is going, sensors. And I don't mean my iWatch, which tells me my blood pressure. That's great, wonderful, I'm so happy to know that. Sensors inside the body is really the future, I think, of nanotechnology. You can make them small, you minimize an inflammatory reaction. You can also incorporate electronics into these sensors to tell you in real time what's happening to an implant. So just a real quick example of this, we take a hip implant, we're growing carbon nanotubes out of the surface, like blades of grass. Those carbon nanotubes can measure the electrical properties of cells that attach. So bone cells have different electrical properties than bacteria. Bacteria have different electrical properties than inflammatory cells. So you can identify what cell attaches and what tissue is growing based on these carbon nanotubes. So we're able to detect that. We're working on technology that can use radio frequencies to send this information to a handheld device, send it to your surgeon, so that you know in real time, do you have 1,000 bacteria right here? If you do, we also developed a polymer. It's basically a polypyrrole, which is conductive in polylactic glycolic acid polymer, copolymer, that degrades under an applied electromagnetic field. So you could put nanoparticles in that polymer to release selenium nanoparticles to kill bacteria that you've sensed in that area. And then without removing the implant, without any other diagnostic kit, you can see, did that work? If not, let's try more. release of antibacterial agents. Until we completely clear the infection, then we can release bone growth agents to increase bone growth in that area. So this allows for an interactive implant. This, again, this is not occurring today. In fact, I'll leave you with this question. Right in the stairwell walking down here, the lights went on because there's a sensor. The car I drive has about, I think, 300 sensors. It's a Toyota Prius. Great, keeps me safe, keeps the car running fine. Something like helping humans, helping human health. The hip implants inserted today have 0 sensors, none. I mean, these other fields have moved so far in advance of sensors, and we're kind of stuck in the dark. So I do think there's a lot of academic research going on. There's a lot of startup companies in this area, and I'm convinced in the next 5 to 10 years, we're going to see implant after implant incorporated with these sensors. Maybe not these sensors, but some sort of sensor that can determine tissue growth and how well that implant is performing in the body. All right, so hope I gave you a little couple of things to think about. Most certainly, I do hope we as a community at some point sit down and really think what happened with COVID and try to come up with solutions that keep this from ever happening again. I mean, we can kill viruses. It is not beyond our capability. But yet, this case just totally wreaked havoc. And nanotechnology, I hope I gave you some reasons how nanotechnology has been used in that area. I hope I also gave you some ideas of getting away from an old-fashioned hospital system. Certainly these sensors that are being developed, these intelligent materials, you don't have to go into a hospital for this. So sensors, getting away from those kinds of technologies. Of course, having just implants that have nanotextures in the first place can really help with tissue growth and implant performance. So, here's my big statement there at the end. Acknowledgements for funding. And I do want to thank, all of the wonderful students that have worked in my academic labs throughout the years. I'm still supervising some students at other universities, but really now I'm focusing attention on commercializing the good ideas that came out, the ones that hopefully will create a change in medicine. And most importantly, thank you guys. If you ever think of a way we could collaborate, if you're ever interested in entrepreneurship, please don't hesitate to contact me. I know you guys have some great things going on here that would be wonderful to be a part of. But thanks for spending time.
So thank you very much, Tom, for this inspiring talk. And now it's time for questions. So please, I will bring you the mic so that the people... No, but for the online.
Yeah, because it's on the internet too, yeah.
So thank you very much for your talk
Thank you.
and for all the things that you have done. It's really impressive. And I am a little bit far from the field of, I don't really understand how you can make the cells or bacteria or whatever grow nanoparticles. Do they normally do something like that in nature?
Yeah, especially bacteria. So there are a lot of just bacteria naturally that make iron oxide nanoparticles, selenium nanoparticles. So they usually occur at a size range that is not large enough for us to really use it. So we just need to add a couple of more ingredients to make that concentration large enough to have a nanoparticle large enough. Sounds weird to say that.
Yeah,
but
like a farm of bacteria that you...
But there are a lot of natural bacteria that naturally make nanoparticles.
Thank you.
Yeah. And I should say too, there are a lot of research groups taking nanoparticles, functionalizing them with chemistries that can attach to certain bacteria over other bacteria. And this, you can do the same thing here, but you get this mixture of proteins, not a specific peptide that some people are exploring. So we think, it's you could remove that chemistry and just have a cell make a nanoparticle. Have the cell make the nanoparticle that you want to kill is the idea. It sounds counterintuitive, but Hopefully it makes sense.
I would like to ask, have you how can you control the coating of the screws with nanoselenium? When you screw, how they survive and they are not detached from the nanoselenium is not detached from the screw itself.
That's right. Great question, and we definitely see in that particular study, I didn't mention it, those screws were nanotextured before the selenium was put on. So if you think of some of those images, you have this feature. So probably the selenium that is surviving the screw implantation is in between. It's in the crevices. It's in the cracks. Yeah, I don't want to say cracks. The air, yeah. So it's protected whenever you screw that implant in. But it is a great question because we're trying to figure out how to remove the selenium that is more likely to come off during insertion. Because we don't want free-floating selenium nanoparticles, right? We want it on the implant. So we're trying to think of ways now that you can really remove the selenium that is protruding, keep the selenium that's more in the crevices so that it can survive that implantation. That study, by the way, was done in Australia, and we were talking about this before. So selenium, have you guys ever thought about selenium?
I was just wondering,
Why selenium? Yeah, of all the things on the periodic table, why are we doing so much work in selenium? So one of the reasons is because I think it was maybe in the year 2000, there were a lot of clinical studies coming out relating selenium to your health. So selenium is part of some foods that we eat. Not a lot, but you do need a certain amount of selenium every day. These clinical studies were showing people who did not have the daily requirement of selenium were more likely to develop cancer. So selenium has been tied to a lot of anti-cancer work. And if you know anything about anti-cancer work versus anti-infection work, there's actually a lot of similarities, right? Reactive oxygen species kill cancer cells. Reactive oxygen species kill bacteria. Theranostics, right? The field of nanotechnology where the same particle can diagnose and treat, can work for cancer and can work for bacteria. So gold nanoparticles can heat up under near infrared, kill a tumor, can also heat up and kill infection. So because of those connections and because of some of the clinical studies that came out, and quite honestly, nobody was working with selenium in medicine, so we thought it would be unique and novel to do so, started a whole big effort in selenium in my academic lab, and now we have 2 companies that have formed to commercialize selenium. The FDA just approved, not our material, unfortunately, but just approved a dental implant that has been coated with selenium. So the FDA is viewing selenium, at least in that application, as safe. So we think that's wonderful for many of these other applications that we're looking at. Another element on the periodic table that's bizarre that we're working with, I think, is cerium. Cerium. So cerium actually has wonderful biological properties. And it has an ability under certain pH levels to secrete reactive oxygen species. Under other pH levels, it absorbs reactive oxygen species. So if you think about, some chemistries, nanochemistries, produce too much reactive oxygen species. It'll kill the bacteria, it'll kill the cancer cell, but it'll also kill the healthy cells. So if you're able to understand what too much ROS is and you're using cerium or cerium oxide, ceria, then maybe you can absorb some of the too much reactive oxygen species. So yeah, there's still, it's amazing to me when you look at the periodic table, you can go across, okay, lots of studies, no studies on health, right, on human health, right? Certainly lots of studies in other applications. And you can find some really neat elements to study, I think, especially in nanoparticle form.
I had another curiosity at
Yeah.
the beginning when you said that okay, the hospitals are not the
Old-fashioned.
best thing, old-fashioned and everything. What is your vision of what we should have? I mean, because we are not only different because we are different sizes, different whatever, but it has to be very specific, the therapy for each of the patients.
Yeah.
And what would you, I don't know, what's
Envision.
your view? Yes, what's your view?
Yeah, and I realize saying, we need to get rid of hospitals is probably not a popular thing to say, but I think we need to think about more healthcare that you can do at your convenience, right? So a lot of people have this idea in nanotechnology where, phones are advancing very rapidly. Wouldn't it be wonderful to have phone technology? And Apple is looking at this. I don't know about Mitsubishi, but Apple is very closely looking at turning this, adding healthcare monitoring. And again, not blood, heart rate, not the things that we can already do with these devices, but could you scan your heart and see if there's a blockage in your aorta? Could you scan bone next to an implant and see if there's an infection? So these kinds of technologies is what I envision in the future, where now granted not everybody will always be able to afford something like this. So I think there will always be a need for some sort of central healthcare location.
Yeah, some brains.
Right. But I think for the most part, the better job we can do to give the patient their own ability to determine their health, I think you'll see a lot more people analyzing their own health. And I think that will help healthcare overall. It'll certainly help their health rather than waiting for an appointment or going through some of these barriers we talked about. But I think where we will really see this is incorporated into handheld electronics that can monitor certain parts of your internal health system.
And then you also need a lot of education
Yeah.
for the people.
Yep. And well, so there's a hope. So the problems,
Yeah.
education, other problems. So we talked to the FDA about this last sensor I showed and incorporating it into, iPhone technology. So education is important. There will always be connected to a clinician, right? So that's critical. In fact, I don't even know how much information you want to give. There's certain information not to give to the patient, but only, I think, give to the clinician to then share with the patient, right? Other issues, security, data security, right? What if you're working for somebody who you're walking down the hallway and they scan you and they see you have bone cancer? Are they going to do something about your job? Is your job secure, or they know that you're going to be out sick for a couple of years? So I think there's healthcare security that's an issue. I think also in these implantable sensors, how do you keep somebody from activating my sensor, right? If Jose wants to put me to sleep, right, can he just punch a couple of things and then so there's a lot of other, I think there are answers to those. I think the bigger challenge is how do you actually develop the materials to have a sensor that are friendly, biocompatible inside your body. A lot of the sensors used outside the body, you could never implant those because they're made of toxic chemicals, right? So I think that's where I see the challenges are right now, is how do you create these sensors? How do you get them to function in the body efficiently? And then I think these other issues of data security, patient knowledge, who to inform, health security, information sharing. I think those things can be straightened out after the science of the sensors are developed.
Thank you.
It reminds me too, and sorry, I'll stop talking, but you probably know Google has a contact lens. So they're not widely used, and I think because they're not FDA approved yet. The contact lens that Google developed takes your tear. You have a lot of information in your tears, believe it or not. And you can use that to determine something called lactic acid. Lactic acid spikes right before you have a heart attack. So their sensor can determine lactic acid, it can determine pH, it can determine insulin for diabetics. So we're already getting there. The difference is those Google contact lenses, they're not really inside the body. They're still collecting information from a tear, which is great, but you have so much more information in your body than even tears or sweat or saliva does. So it's happening, right? And it's going to be great to see what happens over the next 5 to 10 years with sensors in medical devices, I think.
Okay, if there are no more questions, we thank the speaker again. Thank you very much, Tom.
Thank you, guys.